Hello, and welcome back to the final part of the basics of accelerometer calibration. I am, once again, Patrick Timmons, and without further ado, let's continue with a little bit of a recap from where we left off last time. We had talked about reference sensitivity, frequency response, kind of the two main things we look for in a recalibration. We also talked about resonant frequency linearity and a few of the electrical calibrations, the output bias, the ZMO, and the time constant. What we did not talk about was transverse sensitivity. So that's a little bit what we'll talk about here in this last section. What is transverse sensitivity? Well, it's kind of what it sounds like. Transverse is not in the direction that the sensor is intended to measure in. So if, as for in this example down here, you have a sensor that should be measuring up and down on the screen, when in fact any motion that it sees in the transverse would be left and right. So up and down is how the sensor should measure. If it's moving at all in the left and right direction, we call that transverse motion. It's perpendicular to the motion of the sensitive axis. And why transverse motion matters is because this sensor, although it is designed to measure only in the vertical direction, actually has some output, some voltage output from this sensor, charge output from the sensor, when it's moved in that transverse direction. So if you are vibrating in a field that you expect to be measuring up and down, but there's a ton of left and right, transverse motion, there is the potential for a significant error in your measurement because you're measuring a thing that you think you're not measuring. So how is that expressed for a sensor? There's a thing we call transverse sensitivity, and that is how sensitive your accelerometer is to transverse motion. And we express that as a percentage of the axial sensitivity. So you have some output out of the main axis, you also have some output out of that horizontal axis. And as a percentage, it's the ratio of those two. And to get that measurement, we use something like this. Really, there's a couple methods. Some of the original things that were used was just like a typical calibration shaker. And you, in order to excite the sensor, would just put that the sensor on what is effectively a little L bracket. And for your viewing pleasure, I think I'm going to draw it really poorly on the screen here, so my apologies, but we'll use the pen as a pointer. Oops. And yeah, so if you can imagine an L bracket like this, and underneath it we attach it to some sort of shaker. And that shaker is going to shake this little L bracket up and down. So we have this kind of vertical upright here, and rather than putting our sensor on this shaker, the shaker is going to shake up and down here. Rather than putting it on the shaker aligned with that axis of motion, we can just place the sensor on the shaker perpendicular. So we'll put our sensor on there, we'll put a little connector on it. And as you can imagine, this thing is designed to be measuring, in the case of this page, left and right. So if we put it on that shaker, we can shake it upside down and we can measure across the left and right of this accelerometer. And so that works pretty well for that one measurement. But in order to really characterize this sensor, the sensor is in 3D space. It's not in 2D here. So this vibration would be one measurement. We would then have to rotate that sensor. Again, terrible picture, apologies. Rotate that sensor about that upright, that L bracket upright, and you'd maybe rotate it, as fine in degrees as you wanted to, every 1 degree, every 15 degrees, some sort of degree rotation, and then you'd shake it again. Rotate, shake, and you'd get through 180 degrees on that sensor, and you could then begin to determine what the transverse sensitivity is. So the quicker way that we've come up with to doing this is to actually use this thing down below that's a transverse sensitivity calibrator. And what it does is you mount the sensor on top, and you have XY accelerometers. You can see those on here that are going to measure the acceleration in the X and Y direction. And you have your accelerometer that's designed to be measuring up and down, but you're actually going to be shaking it in that transverse direction. To do this, we use a set of piezo actuators to hit a resonance in this vertical beam here. And when that beam goes into resonance in rotation, we get a lot of output here. This R here is the radius, the circle or orbit that sensor is going through. Kind of the key thing to note about this is that we're not spinning this plate up top. We're just rotating the rod. And so if you look at the connector on the shaker here, it stays in the same orientation as that sensor orbits around this radius. That's important because as that sensor rotates around that radius, it's going to have an acceleration vector pointed opposite of this R arrow here, pointed towards the center of the circle. And because the accelerometer is not rotating, it's in a fixed orientation with the cable there, the acceleration vector rotates around the accelerometer, proportional to the accelerometer. It's around its external radius there. So it's equivalent to rotating that accelerometer in this static field, the shaker field that I pictured up here. So what you get is transverse input into this accelerometer through 360 degrees of motion, or 360 degrees of distance around that sensor. And the output that you see from these guys looks like this. So whether you did it on a shaker or whether you did it on an orbital calibrator, you'd see an output that looks like this. And for this type of plot here, you can imagine the accelerometer is mounted in the center of this plate, or the center of this polar plot, going in and out of the page. So the direction that this accelerometer is intended to be measured is through the page, up and down, through this plot. And the outputs that you see in blue there is the percentage transverse sensitivity with respect to orientation. So 0 through 360 degrees of orientation on this accelerometer. That means that there is one direction on this accelerometer that has a maximum, and then there's another direction on the sensor that has a minimum, right? So if you were testing this on the L bracket on the shaker, and you just so happen to line up the accelerometer rotationally with this minimum axis, you'd actually see very low transverse sensitivity, almost none. Whereas if you line it up with the maximum axis there, you would see the most output. So when we define what is the transverse sensitivity of an accelerometer, we define it as the worst case scenario. What is the peak output that you'd see on this polar plot, which in this case, each of these rings is about 0.5%, it looks like. So we're just over 2%, maybe 2.2% for the transverse sensitivity for this specific data set here. And that tends to be roughly what you see. Usually it'll be specified as less than 5% for transverse sensitivity. So, why does this matter? Why would you care about this? First off, I mean, just for the sensor itself, not even to speak of calibration, a lot of times you'll get some sensors in the world out there that exist that have a little red dot on them, and that dot is typically aligned to the position of minimum transverse sensitivity. So on the side of the can, right here, you have a little red dot that is along that minimum axis, and that means that you could orientate that sensor such that during your test, if you know you're going to have lots of motion in this direction, then you can line it up with the minimum transverse sensitivity and have the smallest effect on your measurement. So it's advantageous to know not just what the percentage of the maximum is in the case of transverse sensitivity, but also what is the orientation with respect to that sensor casing. So it's good information to have in the test world. In the calibration world, it's also going to show up as a measurement error. And we did a little test to show this. This is a typical flexure vibration exciter. These are used very widely in the structural test world, also in the calibration world. And it's a little bit different from the other type of shaker that you'll see here, the air-bearing shaker, in that a flexure shaker just has rigid or semi-rigid flexing members that connect the outer body of the shaker to the moving armature here. And as the coil in that moving armature develops force and moves up and down, the flexures are just going to bend up and down. So you have a flexing in the flexures, and what you'll see is that flexing, if at all asymmetrical, is going to cause some transverse motion in the shaker. And so to get around that, we've designed in the past an air-bearing type shaker here, and it's used very widely in the industry these days, the use of air bearings. And what that is, it's the same type of armature that you'd have on the shaker here. You have like a cylinder for the armature. Outside that cylinder is another cylinder that is the air bearing itself. So on this air bearing, you have an interface of a cylinder that's going to develop a film of air, a very, very small gap of air in between the moving portion and the stationary portion here. And so it's to serve as a means of preventing the armature from moving in the lateral directions, in kind of that XY direction laterally, but allowing it to move along the axis of that cylinder up and down vertically. So it's a great way to prevent lateral motion, yet still allow the system to move up and down. And to support the armature vertically, in the case of this air-bearing shaker, we actually use a DC coil to levitate. So to set that initial position, we just raise it up with a DC force there. So you have your XY reduced quite a bit, your transverse reduced with an air-bearing type shaker. And you can see kind of the effect on the data here. So for your exciter, you're kind of interested in what that transverse motion is. It's something that is actually defined in ISO 16063 as a recommendation for really what your value for percentage transverse should be in different examples and different frequency ranges. So depending on the uncertainty of the calibration that you're interested in achieving, it gives just some general guidelines for what percentage transverse you should look for in a shaker. And that percentage transverse, as in how much does the shaker move laterally, is defined oftentimes just by putting a triaxial sensor right on the top of the shaker at the mounting point and measuring out of that triax the root sum square of the x and y relative to the z. So the z would be the up and down direction, the x and y is the lateral direction of the shaker. And so you can express that as a percentage transverse motion. And when you do, you get plots like this with respect to frequency. This is data here in blue on a flexure shaker that we did with that same methodology. And the vertical scale there is transverse motion, percentage of axial. So it's expressed as a percentage. Horizontal, of course, is frequency. And you can see there's a few points on here. Well, you have these little modes of vibration. There's a big one here at about 3,500 hertz, and they continue out into the higher frequency realm. So this is up to 10 kilohertz on this plot here. So at certain points, you'll have these modes of vibration where you have a lot of X and Y motion for a given Z motion. And so as a percentage, if you think about that, 100% here means that if you're running, say, a 10G acceleration sweep, at 3,500 hertz, you're actually going to have 10 Gs of lateral motion. And it can actually be higher, which means that your X and Y motion is actually higher than your Z motion. So you could have 20 Gs, or the peak is probably up here close to maybe 25 or 30 Gs of lateral motion when you're commanding and telling your test to run a 10G sweep. So you can see that when you have these big spikes like this, it starts to become important as to that transverse sensitivity on your accelerometer. Your accelerometer is going to respond to this motion, and that is going to show up as an error in your measurement. So what we did here is kind of a nice test to visualize what happens in that type of test. So we have a typical back-to-back calibration like we saw. We have a reference sensor on here, and we have a small teardrop test accelerometer on top of the shaker there. And with a little adhesive mounting plate, we can actually adhesively mount this teardrop on here and then rotate it. Adhesively mount it and rotate it. And for each rotational position that we might have that cable coming off there, we can take a data set of frequency response. So we will calibrate this little teardrop with that cable in different orientations on the shaker. And what you get is a plot like this. And so this is what you'd see on a cal report. This is a calibration result. Voltage sensitivity, millivolts per G on the left there. And that's how much output you have out of your test accelerometer with respect to frequency. So the interesting part is that all these different traces are those different orientations of the placement of that accelerometer on the shaker. And you can see at certain frequencies, you get very different sensitivity readings depending on the orientation that you have it in. And what you'll find is, you know, if we just look here, if we look at the bottom axis, and there's 3,000, that's about 3,500 hertz. We have a big variance in sensitivity reading, and 3,500 hertz, as we just saw before, is the point where we have that big flexure-induced transverse mode. So that transverse motion is being picked up on the accelerometer and producing much higher output. So what's happening here in this turquoisey color, 90 degrees, right? There's a specific orientation that we ran into when we were rotating that around where we actually got a pretty flat frequency response on this accelerometer. And really what's happening, if we go back a few slides here, is just this plot here. Is that test accel, that teardrop that we're rotating, we're effectively rotating this blue curve here, this polar plot. And that shaker, if you can imagine this outer circle here is the top of that shaker, physically that shaker is going to have some vector, some direction in the XY that is going to be the dominant rocking mode for that shaker. So it's going to be perhaps rocking in this direction. So you'll have a ton of motion, in this case up and down, on the shaker head as it's vibrating. So it's going to be kind of vibrating in and out of the page, but because it's rocking, you have a large motion here, even greater than the z-axis. And so when we rotate that teardrop, we're rotating the blue graph as well, because that transverse sensitivity on that specific test accelerometer is fixed. When we hit this minimum here, if we rotated this just a little bit farther clockwise, we'd hit this minimum, and that's where we get a plot like that plot that happens to be 90 degrees in this case. We get a very minimal effect from transverse motion because our sensor is not sensitive to that rocking mode. And as soon as we rotate it off, back towards 60, for example, you get more output. Back towards 30, you get a lot more output. And so we're rotating that curve closer to the peak of that transverse mode. So we're lining up this axis of the blue circle with that rocking mode. So depending on how you rotate and place your sensor, you can get different frequency response output out of your accelerometer. So this has to be accounted for when you create an uncertainty budget for your calibration. And the transverse modes, as you can see, this is 10 millivolts per G, this is 9.5 millivolts per G. It's a big influence on uncertainty at that frequency. So in your cal reports, you'd often see stuff like this. You'd see a little blip, drops down, and then it pops back up, and then it kind of settles back into a normal. And what's happening here, again, 1,000, 2,000, 3,000, 3,500 hertz, you get this little blip here in your cal result. And it depends really on the density of the points that you're testing as to what the shape of that is going to look like. So if you land right on that frequency, you'll have a very high output potentially. Or if you skip that frequency entirely, this could look like a flat line. So the density of your test points can affect whether you see that or not. And so we did the same test here on an air bearing shaker. And spoiler, back on this plot here for transverse motion, the green and the red line at the very bottom there are actually the percentage transverse motion of an air bearing shaker. So it's very, very, very low transverse motion in proportion or in comparison to a flexure shaker. So exact same test, exact same rotation, this is the result. So a very consistent sensitivity value you get on your sensor that is really kind of independent of that rocking mode because it doesn't exist, right? No rocking, which means no transverse output in that range. Kind of cool. So kind of wrapping up here, some of the standards that you have, obviously ISO 9001, if you want to look up some of the stuff, this is of course the obvious one. It's a company-wide quality management system. If you want to get specific, if you want to get accredited for these types of calibrations, or if you want to look to see that the calibration lab that you're getting your assets calibrated in is competent in calibration, the relevant standard there, of course, is ISO 17025. There's a lot of accreditation bodies that will go on site to your facility or to whatever facility is doing the calibrations and audit you for your ability to deal with issues that might happen during a calibration, make sure that you're reporting your uncertainties correctly, make sure that your certificates are set up to convey all the relevant information for an ISO 17025 calibration. So that's kind of the main thing you want to look for is one of these labs accrediting your calibration provider to ISO 17025. And if we get more specific than that, if we go into the calibration standards themselves, we have the ISO 16063 series, which is in multiple parts. There's part 11 and part 13, which are primary standards, and then part 21 and part 22, which are the secondary standards. And those each have to do with shock and vibration, or vibration and shock. So each of these is going to detail the types of calibration, the exciter that you use for different types of calibration, signal processing, and uncertainty, all the nitty-gritty details on the calibration methods in that ISO standard. So these are kind of the go-tos for the individual calibration types that you'll see out there. And lastly, I'll kind of talk about uncertainty here. When you are doing or receiving a calibration, if you're calibrating yourself, one of the most important things to include with that calibration is not just the sensitivity of your test device, but what is the uncertainty of your reading. So if you give some value, it's pretty meaningless unless you say also how uncertain you are about that value. And the kind of egregious example I always like to give is like a gas pump. As a consumer, you always expect that when you pump a certain amount of gallons of gasoline, you're actually getting that amount of gallons of gasoline. So, you'd be pretty upset if you pumped 10 gallons of gasoline, or this even works in metric, 10 liters of gasoline, and or petrol, we'll call it petrol, into your vehicle. That's what the reading on the meter says, that's what you pay for. But in reality, if you got half of that, if you got 5 gallons or 5 liters, that wouldn't be good. You'd be upset. You'd be getting less than what you expect. And so knowing how close even a gas pump can detect a flow rate or how many liters are being pumped into a vehicle is important. It's the same thing for test and measurement. If you're measuring a vehicle or a structure, there's going to be a certain amount of uncertainty in that measurement, and that's going to affect the risk. When does a component fail, right? How much output do you have on a certain channel that's going to ultimately lead to a fatigue? What's the time to fatigue? How does that change with respect to uncertainty? And depending on the application, you can have very safety critical operations and safety critical measurements that depend on a certain sensor. So knowing the uncertainty of that measurement is pretty important, and it really stems initially here from the calibration. So the calibration that is printed on the report is going to be the beginning of some sort of uncertainty analysis, and down the line in your applications you'll have to do another uncertainty analysis there to determine what the actual test uncertainty is. But for calibration, we typically break it up into 2 components. And that is a systemic component here and a random component. The systemic component is just a bias in your measurement. You can think of how far away you are from the bullseye, with the bullseye being the true sensitivity of your test device. And then you have a random component. That is the distribution of your data set around some sort of center. So it's the distance to center and then your distribution from there. So you can look at repeatability, and you can also look at potential offsets in your measurement to generate that uncertainty. And it's typically expressed in a coverage factor of k equals 2, or 2 standard deviations, giving you about a 95% confidence interval for that data set. And so those 2 types of uncertainties in calibration: systemic, again, involves the higher up portion of the chain, which is the reference accelerometer and signal conditioner uncertainty. What is the uncertainty of the primary calibration of your reference, for an example? Transverse motion of the exciter, this is an uncertainty component that's defined in ISO 16063, part 21. It's going to talk about how do you calculate based on the motion of your exciter. What does that lead to as far as uncertainty? Just drift, if you take an accelerometer, you calibrate it, you set it on a table, and you come back 20 years later, how much has that sensitivity changed over those 20 years, right? We typically break that down into smaller and smaller chunks and say, how much does that change over 1 year? And so you can determine, based on your calibration interval, how much is your reference sensitivity going to change. and then anything in those voltage measurements. So in the two channels that you're measuring voltages in a back-to-back calibration, what is the inaccuracy between those two channels? Types of stuff you'll see in random uncertainty is everything to do with mounting and cabling. This is probably the biggest thing that we see that's inconsistent. Just because things like cables don't hold up perfectly over time, you can get connectors that have issues on sensors over time, and just really how an operator connects a cable or how they use strain relief a cable can have a pretty big effect on the measurement uncertainty, specifically at low frequency. And then the physical mounting of the unit itself. So glue is always the great example there. When you're putting adhesive on a sensor and putting that sensor on a structure for measurement, it's going to have some effect, and it will have that same effect that is measurable in the calibration lab. You know, the amount of glue that you use and the centering of that test accelerometer on your reference accelerometer is going to affect the measurement. And so all these types of operator techniques typically lump into a random component into our uncertainty budget. And that just means that when we calculate an uncertainty for one of our cal systems, for example, we're going to do that over a long period of time. So it's going to take into account multiple mountings of the test asset and multiple operators and even multiple days, multiple months to account for things like the electrical noise over time and varying lab conditions. That's a big one potentially there is how does the temperature in your laboratory change over time. And when you're done, you end up with something like this typically. This is an example of an uncertainty budget. It's going to have vertical columns there that pertain to frequencies. So we have, in this case, 5 hertz all the way up to 20 kilohertz. And along the vertical rows there, or sorry, the rows, the horizontal rows, you have different influences of uncertainty. So some of those are systemic errors, some of those are random errors. And across this point here, about halfway down, we combine these. So below that line we have the combined standard uncertainty, which is a root sum square of all the components above it. And that gives you a k equals 1, or 1 standard deviation of uncertainty there. To express it as a k equals 2, we multiply that value by 2. And finally, we typically publish a little bit higher than our k equals 2 uncertainty. So you can think of it as a slightly higher confidence interval. We always do that to account for anything that we haven't thought of and allow us to make changes and edits to our uncertainty budget without having to change any published documentation on our unit. So we'll essentially be a little bit more conservative with our uncertainty that we state. So thank you for your time. Hopefully you guys learned something about some of these calibration types that we do on sensors and some of the means that we evaluate them and evaluate the uncertainty of those measurements. Thanks again. Have a good one.